So today we are very excited to have Ming back again at the Temporal Graph Reading Group. So Ming Jin is a PhD candidate in computer science at Monash University, where he is currently being supervised by Prof. Shirui Pan and Assistant Prof. Yuanfeng Li. He is also a research staff at Metso Autotech and a research assistant at Monash University. Ming completed his bachelor's and master's degree at Hebei University of Technology and the University of Melbourne in 2017 and 2019, respectively. He has published over 10 top-ranked conference and journal papers and regularly served as a PC member and reviewer of major AI, ML data mining conferences and journals, including IJCAI, PAKDD, TNNLS, TKDE, and more. Ming's research interests mainly focus on graph neural networks and geometric deep learning, with a particular emphasis on temporal settings such as dynamic graph neural networks. He is particularly passionate about applying these techniques to tackle practical challenges such as time series forecasting, industrial process modeling, and anomaly detection. So we are very glad to have you today to present a survey on graph neural networks for time series forecasting, classification, imputation, and anomaly detection. So I'll pass the mic to you.
Yeah, thank you, Andy. Let me share the screen first. Okay. Okay, so thank you everyone and good morning. Today I'm going to share our recent surveys on graph neural network for time series, and I emphasize in two aspects: forecasting, classification, imputation, and anomaly detection. And in today's talk, I will mainly cover three parts. In the first part, I will give a brief introduction of the context, as well as the outline of our proposed framework and categorization. And in the second part, I will give a brief introduction of the graph neural network for time series forecasting, classification, anomaly detection, and imputation. And finally, I will illustrate three most prominent applications, as well as three very excited future directions to work on. And let's get started from the part one. So in this part, I will first introduce the concept of the time series and the graph, as well as the graph neural networks. And then I will give an overview of the GNN for time series, and then an outline of the proposed framework and the categorization. Okay, so what is the time series? So time series is actually a sequence of data points that occur in successive order of some periods of time. And in real world, we know that there are many sensory networks. Like in the highway, we have some sensor installed here, so that can detect some information like the vehicle speed. And for each of the vehicle, they have some unique variables like the brake pedal position, steering wheel angles, etc. So if you combine those information together, you have a multivariate time series like this. So we can actually mine some useful patterns in such multivariate time series data to do some very exciting downstream tasks. Okay, so here are two examples of the time series data that we commonly use in the real world. So on the left-hand side, that's called the univariate time series. So there is just a single variable here that evolve with time. And on the right-hand side, we have the multivariate time series. So in fact, actually, there are more than one variables. So, in this example, we have two. The one is blue, right? And another one is green. Okay, so before we have the very basic understanding of the time series, but what are the graphs? So in real world, many kind of data that can naturally formalize graphs. So for example, the bibliography networks that different articles are set each others. So in this case, this is known as the bibliography networks. And in real world, we also have some entities like the paintings, the artists, and other kind of like the place, whatever. And those entities are actually interconnected with certain relations. And in this scenario, this is known as the knowledge graph. And as I mentioned, the sensor network, of course, like the traffic networks, and there are many other examples that can be abstracted as the graph structured data. And we know that, okay, there are many graphs in the real world, but how we can model the information inside of the graph, that is the concept behind of neural network. We use certain deep learning based approaches in nowadays to do the mining of the information in the graph structured data. So on the left hand side here is an overview. Like given a real world attributed graph, we can use the graph neural networks to learn the low dimensional node feature representations for each of the entity, or say the node in this graph structured data. So this is the most common use case with the graph neural networks in the real world. And regarding the taxonomy, or we say the categorization of the graph neural networks, we normally have the spatial GNNs. So in spatial GNNs, the most popular concept is the message passing. So in this case, given this static graph, and if our target node is the node A, and then how we can learn the representation of this node, we can actually aggregate the information from its neighbors. For example, the one hop neighbor is B, C, and D, right? And the two hop neighbor of A, it could be C, and it could be E, of course. So we can aggregate the informations from those neighbors to the target node, like illustrated on the right-hand side. So this is called the message passing. And more broadly, this type of the graph neural network is commonly known as the spatial GNNs. But before we have the spatial GNNs, we normally define the convolution operators in the spectral domain. So in this case, or we say more traditionally, we define the spectral graph filters to filter the information in the spectral domain. So the first step is transform the signal, the graph signal, that is the X, or we can understand this as the attributive information to the spectral domain by using the graph Fourier transformation condition on the underlying graph topology. So this part, you transport X. So this is known as the graph Fourier transformation. And after that, we define, or we say we learn the spectral graph filters, Y theta, and this normally we approximate it with the polynomials. And the coefficient of the polynomial of those polynomial bases is what we are trying to optimize end to end on the data that we have to learn how to filter the information that we need. So this is the learnable part of the spectral graph filters. And after we filter the input graph information, we cast the filter the signal back to the graph domain by using the inverse graph Fourier transformation like this. So there are actually 3 steps, in conceptually that under the umbrella of the spectral GNNs. Okay, so the main difference between the spatial and spectral GNN are 2 aspects. So the spatial GNN actually act as the low-pass filtering. That means it captures the similarity between nodes in a given graph. But in spectral GNNs, if we have the polynomial basis well defined, that can those graph neural networks in spectral domain that can actually filter the information that beyond the low pass. So we can have middle pass, we can have the high pass filterings, so allowing more diverse information capturing of the given graph. Another difference could be the efficiency, that we know that the spectral GNN may not be well scalable compared to this the spatial counterparts, because for the method department, we have something like graph stage or something that can scale well on large graphs, but that's another story. That's not our main focus is in today's talk. Okay, so we know the basic concept of the GNNs. Now let's back to the time series. Like, we now considering how the concept of the graph can be incorporated in learning the dependencies in the time series data. So in univariate time series, this scenario is most common in the classification problem, that given a univariate time series, how we can learn the representation of this time series. So in some work, we find that the first step is trying to extract some shiplet, or we say some snippet of this given time series, for example, 3 chunks here, and then we treat each of them as a node in a graph that we're trying to construct. And then we use the graph neural network to capture the correlations between those shiplets. And this is known as the series size graph, even though this is very real in real world situations. And on the right-hand side, given the multivariate time series, we normally use the GNN to capture the spatial dependencies between variables. And this is widely known as the intervariable correlation that go beyond the temporal dependencies. So this is more common in the literature, I would say. So in this case, we can use some temporal modules like recurrent neural networks or convolution neural networks. And nowadays we have, of course, transformer-based method to capture the temporal dependencies. And then the GNNs can opt in to capture the relations between different series that evolve with the time. Okay, so regarding the second scenario, the more common situations in the real world, for example, we have such a multivariate time series. Now we want to highlight the underlying evolutions. But how we can do that? How we can transform this multivariate time series into spatial temporal graphs? So there are actually 2 ways to do that. The first one is with the fixed graph structure. So that means given an input window of the time series like this, I learn the graph structure, and in this window, this graph structure is fixed like this. So in this case, only the attributive information evolve with time, but the underlying topology is unchanged. And in the second scenarios, both attributive and topology information change with time. So in recent research, there are more and more works that trying to explore the second situations and find that this modeling may be helpful in many real-world scenarios. Okay, so now we introduce the concept of the graph neural network for time series analysis. It's also known as the GNN for TS. And in this example of the wind farm, we can actually form different analytic tasks like the forecasting, imputation, anomaly detection, and the classification. So the forecasting is very straightforward, that given a set of the historical observations, we are trying to forecast the future states of those nodes. And the imputation, if the case is that I have 2, for example, I have 2 power plants, 1 and 2, but if there are some issues with the sensors installed here, we may have some missing values in between. So actually we can use the underlying dependencies between those variables here to recover the information in those missing parts. So that is called the time series imputation. And for the anomaly detection, I think it's more straightforward. Like for example, in some point of time, the speed of the turbine might be anomalies. So those periods of time, we may tag this as the anomaly, as well as this one, because of this part and this part. So this is the time series anomaly detection problem, and this is very useful in many real-world use cases. And for the classification, that is to classify the status of a certain node at the certain point of time. For example, this is upward and this is downward. So this is the time series classification. Okay. But before we dive into the specific taxonomy that we defined, we haven't discussed the graph structures because this implies that to employ GNNs for time series analyze, it means that the graph structure must be provided. You need to have the graph structure to fit into the graph neural network to do something, right? But in many real-world scenarios, we don't have such graph structures. So this gives us two choices to complement this information. The one is heuristic-based approaches, and another one is learning-based approaches. So the heuristic-based graph is trying to use some humans' understanding, or we say some metrics, to build such missing underlying topologies here. And there were four commonly used approaches. The one is called the spatial proximity. So this is trying to build the graph by using some metrics like the shortest travel distance. So the shorter the distance, the larger the edge weight. That means they are more closely related to each other. So I think this is more coming, it's more straightforward to be understanding the traffic network, right? Like if two people are very close to each other, then they have a stronger connections. And for the pairwise connectivity, I think it's more easier to be understand if two nodes, or say if two, for example, sensors are directly linked, then we flag this as 1, otherwise 0. So in the, again, I think in the traffic network, it's quite obvious, like two connected intersections. Then in the graph, in the adjacency matrix, the entry is going to be 1, otherwise 0. And for the pairwise similarities, that means we can use certain measurements to measure the similarity between, for example, two variables with a time series here, and it could be the cosine similarity or other kind of metrics. And functional dependencies is another choice. For example, you can use the granular causality to measure whether the time series, for example, J can be used to forecast the time series I. And of course, you could use other functional dependencies like the transfer entropy or the discrete physics lag index or many others that you can use. And for the learning-based graphs here, we normally consider two approaches. The one is called the embedding-based approach. A typical example is in the MTGN, and another one is called the sampling-based approach. And the GTS is one of the most representative methods. And for this one, embedding-based, this is a very typical strategies to make it work. So firstly, we randomly initialize two embedding matrices, E1 and E2. And after certain transformations, we have two metrics, M1 and M2. So these two metrics are gonna to be used, after certain operation like the matrix multiplications, subtractions, and nonlinear activations. We use that to directly build the underlying adjacency matrix. So the nonlinear activation here is actually act as certain regularizations, because a typical adjacency matrix has only positive values, right? Like the value larger, equal or larger than 0. So that is why we have some activation like ReLU here. So as you can see that this adjacency metric is directly related to the optimization of M1 and M2. And for those two metrics that directly related to the optimization of E1 and E2, of course, as well as other parameters here. So this is called the embedding based because we're trying to optimize the things behind like E1 and E2, right? And for the sampling based, here the core idea is trying to parameterize certain distributions like the Bernoulli distribution here. And then we do some sampling to sample the graph topology known as the adjacency matrix here, like this. And then this sampled graph structure is obtained in the following spatial temporal operations here. Okay. And then I will discuss the outline of the graph neural network for time series analyze. So this picture shows the general pipeline for time series analyzed by using the GNNs. So given an input, for example, multivariate time series like this, we first do some data preprocessing, like the graph structure learning, data denoising, as well as the normalization. And after that, we need certain pattern machine. But what is that? What is the composition of this pattern machine? This is usually known as the spatial temporal graph neural networks. And it's mainly consists of two important modules. The one is called the spatial modules, consists of several graph operations, like whatever spectral GNNs, spatial GNNs, or the hybrid one. And then we have some temporal modules. And the temporal modules, again, it could be in time domain or in the frequency domain, but whatever. And then we consider the model architecture, like how we can combine the spatial module and temporal module together to do something. And your model could be discrete or continuous. So the continuous means, as you may know, that some recent work that we use the differential equation, right? Like the STD, NCD. So that's just one of the examples. So in those model, the underlying whatever the temporal modeling process or the spatial modeling process are characterized by a specific differential equation. So that is continuous with respect to the time. So that is known as the continuous architecture. But for the rest of the conventional method, most of them are discrete. But beside of discrete or continuous, those two modules could be coupled or factorized. Like that is another dimension, like how we can combine them together to capture the underlying dependencies. And then after that, we have the time series representation. And then by applying certain downstream hat like the forecaster, classifier, anomaly detector, whatever, you can do specific downstream tasks to get your predictions. And on top of that, we have two taxonomies. The one is task-oriented, like what we can do with the graph neural network on time series. And another one is the methodology-oriented. So that cares more about how the technical stats on those existing method. Okay, so for the first one, we have four tasks. The one is forecasting, another three are classifications, anomaly detection, and imputation. So for forecasting, we can do typically multi-step forecasting and the single-step forecasting. And for both of them, we may have short-term or long-term forecasting. So that's if the categorization from the perspective of the specific task. And for the classification, we have univariate classification or the multivariate time series classification. And we have specific categorization here to model the underlying things like series as node or series as graph. I will discuss the details later. And for the anomaly detection, we mainly consider two aspects. The one is how we detect those anomalies. And another aspect, we say the dimension, is how we can interpret our anomaly detection result. We want to know what kind of factors triggered those anomalies. Okay, and for the underlying strategies, that could be based on different discrepancies, like whatever the relational discrepancies, forecasting discrepancies, reconstruction, etc. And lastly, for the imputation, we have in-sample imputation and out-of-sample imputation. So in-sample imputation, if given the data with the missing value, we're trying to find a way to fill up those missed values. But for the out-of-sample imputation, we care more about to fill up the missing values in disjoint time series, or say the sequences. Okay, and for both of them, we can have deterministic or the probabilistic imputations. So this one, deterministic, will give you just a single best value, but the probabilistic one will give you a contribution. Will give you a distribution with the possible values. Okay. And on the right-hand side, for the methodology-oriented taxonomy, this is actually what I have just covered. So we consider three aspects: overall architecture, temporal module, and spatial module. And for the overall architecture, we can do the discrete factorized model or the continuous coupled model. So those are kind of certain combinations here. And for the temporal modules, of course, it can in time domain or in the frequency domain, and we have certain strategies to do that, like the recurrence-based model and convolution-based model, of course. And for the spatial model, it could be spatial GNN, spectral GNN, or the hybrid of both.
For the just a quick question.
Yes.
For the spatial module, it sounds like GNNs are handling it, but how about like graph transformers or so on? Is there any work on those?
Yes. So to be honest, the graph transformer have not been in our first version of the survey, but we are trying to update the current version to incorporate those latest transformer-based method in.
Okay, sounds good.
Yeah, that's a very good question. Yeah. And the second part, the graph neural networks for time series analyzed. So in this part, I will first give an overview of the time series analytic tasks, and then I will focus on four main categories: the forecasting, classification, imputation, and anomaly detection, to give you some examples as well as the underlying ideas behind. Okay, so here's the GNN for time series forecasting and overview. So given the input time series, our first step here is building the graph topology, and then we employ a spatial temporal GNN here, denoted as the F theta, to get the time series representation, and then we apply some forecasting hat here to get the forecast. And our predicted result with the ground truth here, we're trying to calculate the forecasting loss, and this is very straightforward. And for the classification, the situation becomes a little bit complex here. So here gives two examples actually to illustrate how we can classify a univariate time series. So the upper branch shows the ideas behind the series as graph. So given a univariate time series here, we extract three shiplets, and the first step is building the graph topology. And then we employ a graph neural network to capture the correlation between those shiplets. And then we apply a pooling layer here. The pooling layer will help you to get a global representation of this time series. So that is to aggregate the representation of these three shiplets, denoted as the node in this graph. And then we use this graph representation as the final representation of this time series and passed through a classifier to get the prediction. And on the bottom level here, this is known as the series of nodes. So the underlying concept is that your data set normally have more than one data sample here. And we can use the information from other data sample to help the classification of a specific time series. So in this case, the green, orange, and blue time series, those are three different data samples can actually be formed as the graphs like this. So 3 nodes here, and then we use a certain graph neural networks here to gate the node representations like this. And in this example, if you want to forecast, if you want to classify the label of this green node, we have its node representation like this. And then passed through a classifier, we can have its label predicted. Okay, so this is the most important concept behind the time series classification. And for the anomaly detection, again, given the input time series, we have the graph structure learned or constructed. And then by employing a spatial temporal graph neural network as the embedder, we can have the time series representation again. But here, we will employ certain reconstruction modules. And for example, we can reconstruct the underlying graph topology, or we can do for example, forecasting, and to do something like the reconstruction discrepancies calculation as well as the relational discrepancies calculation, or I combine them together to formalize the final calculations of the anomaly scores of the data point at a certain time like this. And lastly, we have the time series imputation. So given the input time series with the missing values here, our first step again is the graph structure construction. But be aware there were some missing values in the data representation like this. But the key concept behind of the GNN for time series imputation is that we can actually use the intertemporal and intervariable dependencies to fill up those spacing values, because we believe, for example, those orange cell and blue cells or some historical information like this one and this one maybe benefit in recovering the missing value in this part. So that's the basic ideas. So after we obtain the time series representations, we can employ certain imputation modules. For example, just a sample, for example, message passing layers or feed-forward neural networks. It can help you to get some values on those parts without the ground truth values. And then you could do the certain optimization like this by comparing with the ground truth. So that's the basic idea of the GNN for time series imputation. And
just a very quick idea for just a very quick question on imputation. So it's a very naive question. Do we know exactly how many data points are missing beforehand during training, or you only know that during evaluation? Like, how do you know something is missing here?
Okay, so one typical scenario is we can actually construct the training set to simulate the scenario with the missing values. So normally based on your experiment settings, you may set some missing value rates here and do the training like this. And then you evaluate on the real side, for example, with the missing values. I think that could be one of the typical scenarios to do this task.
Okay, so basically during training, you have placeholder tokens saying that this is missing in the time series.
Yes, something like that. So that makes this pipeline works. So otherwise you don't have the ground truth. Yeah.
Okay, so you can't kind of change the number of things you want to inject at test time. You will know that there are 3 missing during training, and you predict 3 at test time.
Yes, but I think be aware. I think this is just one of the typical scenario that we can train the whole things. But in some recent work, we observed that there are other situations like the problem definitions here, like to train the things. And I'm not very sure, but I think there could also be the way like to do the things in self-supervised or even unsupervised manner. Yeah.
Right. Thank you.
No worries. Yeah. And then I'll mainly discuss the time series forecasting. Okay, so for those branch of method, our categorization is mainly based on the technical aspect, because most of them are doing the similar task. For example, the short-term traffic forecasting. So from the technical point of view, as we mentioned, we focus on three aspects: the intervariable dependencies modeling, intertemporal dependencies modeling, and the architecture fusion. Okay, so here is the summarization of the most representative forecasting method that's based on the graph neural networks. And in this table, we see there were several notations here. So for example, task. On the left side, the M and S denotes the multi-step and single step. And on the right-hand side, the S and L denote the short-term and the long-term forecasting. Okay, and for the architecture column, the D and C denote the discrete and continuous model architecture, and C and F denotes the coupled and factorized. Okay, and for the spatial model, I think it's very straightforward, spatial or spectral GNN. And for the temporal mode, T denote the in the time domain. And there were some of the work like this one and this one that operate on the frequency domain. On the right-hand side, there were different notations like R, C, A, and H. So R is for the recurrent based network, C for the convolution based network, and attention based, and the hybrid of more than one. Okay, and for the missing value, that denotes whether a method can naturally handle the situation. For example, if you input have some missing values, whether those forecasting methods can naturally handle that situation. And for the input graph, the R denotes the required, and O denote the optional. So the optional could be it's not purely relied on the given graph. If you don't have it, can learn that end to end. But if you have, that can be naturally incorporated to boost the performance. And NR denotes the node required. Okay, and for the learned relation, there were some cell denoted as S, and two of them denoted as D. So F means the static. The underlying graph topology is fixed for a given, for a certain window of the input time series, and D denote the dynamic. So that's what illustrated in the previous slide. And the graph heuristic, as we mentioned, there were several of them, like the spatial proximity, SP, PCE is the pairwise connectivity, and for PF and FD, pairwise similarity and functional dependencies. So that's a brief summary of the existing GNN-based forecasting method. And here, I will mainly discuss 6 of them. So those are very typical examples that cover different aspects in our mentioned, for example, under our categorizations. For instance, STEAM GNN that use the spectral GNNs, and it operates, I mean, in terms of the capturing of the intertemporal dependencies, it operates on the, it operates in the frequency domain. And for the DCRN, it used the spatial GNNs, and its operation, on the other hand, is in the time domain, right? And there were also some work, for example, using the convolution models instead of the recurrent model, like the STGCN, and some models based on the attention, like the G-man. And for the architecture fusion, for example, we have some work based on the discrete fact-derived neural architecture, like the MTGM. And we also have some work based on the continuous coupled architecture, like the MTG-ODE. So I will begin from the STGCN. It was proposed by ETL in 2018. So in this work, this is the high-level framework, right? So given the input time series, as well as the weighted adjacency matrix, we have several spatial temporal convolution blocks here. And in each of the block, we overlap the temporal and spatial convolution here. And for the spatial convolution, in this work, it could be the chip count or the first order approximation of the chip count that makes the GCN, right? And for the temporal convolution, they use the 1D temporal convolution. So it's actually convolution based. And as you can see that the temporal module and the spatial module are actually overlapped with each other, one by one processed. So this model is actually under the category of the discrete factorized. So this is how we categorize an existing method. And another example is the DCRN. So in this case, if you have a look of this overall architecture, you say, okay, it's based on the encoder and decoder architecture. And in each of them, the core component is known as the diffusion convolutional recurrent layer. How it's defined? Here is the formula. So if you have a look, you could find this is, I mean, the framework of those equations are GRU, the gated recurrence unit. But the key difference is that we have the graph convolution embedded inside three of them. So in this case, we have the spatial and temporal module fused together. So this is known as the coupled neural architecture. And of course, it operates in the discrete time. So this is known as the discrete coupled model. And for the spatial module, it uses the graph diffusion. It remains the low-pass filtering. This is spatial GNN-based. And for the temporal module, it uses the recurrent neural network, the GRU. So it's recurrent-based. Okay, so this is another example. And for the Gman, in this example, this is the overall architecture. So again, it's also based on the encoder and decoder architecture. And the core component is known as something like the spatial temporal attention block. And it looks like this. So given the information, there were two attention mechanisms here. The one is known as the spatial attention, and another one is the temporal attention. And those two operations are operating parallel before fused together. So this work is also a kind of discrete coupled neural architecture. And here's is the illustration of the spatial attention that actually capture the dependencies between a specific node with its neighbors. And it's more or less related to the graph attention networks. And for the temporal modules, we attend to the historical information of each node itself. So this is actually a very typical vanilla attention-based mechanism. So this is attention-based for the temporal module. Okay, so so far, these three examples are very straightforward. And for another work, Steam GNN, so this is also very classic. That's given the input time series. We learn the graph structure, of course, and then we have several blocks known as the Steam GNN block. So how those blocks are defined? Here, as you can see on the upper branch here. So given the inputs information, we first cut them from the original graph domain to the spectral domain. And then we have some operations to capture the temporal informations, and then the graph, and then the spatial dependencies. So this is also interacted with each other, or we say overlapped with each other. So in this case, they were factorized. Okay, so this model remains discrete factorized. But the interesting things is that both of the operation, whatever the graph neural network, as well as the temporal modules, they operate in the frequency domain. So the graph Fourier transformations will bring this, will allow us to capture, or we say to do the graph convolutions in the frequency domain, as we mentioned at the very beginning. And for this spec sequence cell here, as you can see, there was some operation known as the discrete Fourier transformation, and then followed by a convolution operators, and then the inverse discrete Fourier transformation. So this allows you to model the temporal dependencies in the frequency as well. So this model is actually a purely frequency-based model. So the spatial model, for example, is the chip count, and the temporal model is the convolution operation in the frequency domain, but using the Fourier transformation. And another work, MTGN. So I mentioned this work here, meaning to show you like how we can simply do the spatial temporal learnings by using a very typical discrete factorized model. I think compared with the aforementioned method, I think this one is more straightforward. As you can clearly see that the temporal module and the graph convolution modules operate one by one like this. And then there were some residual connections together with some skip connections. It allows us to effectively model the underlying spatial temporal dependencies in a given multivariate time series. And the spatial model here is the mixed hope message passing neural networks. This is actually in the high order that allow you to go beyond the low pass filtering. And for the temporal modules, it uses the dilated temporal convolution. So it's also convolution based. And this one is actually a continuous version of the MTGN. So how it differs from MTGN? So given a time series, it's actually an input multivariate time series. We first learn the graph structure, and then we map the signal to the latent space. And then there were two processes defined. The one is called the continuous graph propagation, and another one is called the continuous temporal aggregation. So these two processes are actually formulated within a single differential equation. So we solve that differential equations. We doing the spatial temporal dependencies modeling. So this model is actually continuous coupled. So that's the key difference here. And for the spatial module and temporal module, there is a separate differential equations to do this part, and another differential equations to do the temporal module. But finally, those two are fused within a single one, like to solve the whole process. And after we have the time series representations like this, then we can have some forecasting head that known as the end convolutions to help you to gauge the final forecast. Okay, so far we have covered several very representative works in the time series forecasting, and then the time series classification. So here we consider two scenarios. The one is univariate time series classification, and another one is multivariate time series classification. So for the first one, as we mentioned, we consider two scenarios. The one is series S graph, that is transform a univariate time series into a graph to identify the different patterns in different chiplets. And another one is series S node that's shooting the information in other time series samples in a data set. And for the multivariate time series classification, that's more or less related to what we have discussed in the forecasting method. I will also give you an example related to that. So here is a summarization of the existing method. And as you may be aware that there were just a few of them. So this area is still underexplored. So the task here, M denotes the multivariate and U denote the univariate, and the conversion is quite straightforward, right? So okay, so here I will introduce three representative work. The one is called the time to graph plus, and in this work, given a univariate time series, for example, the electricity usage here, we will divide this time series into several shiplets. For example, shiplet number 40, and then we learn a graph structure like this. Okay, so in short, each time series, okay. Okay, there were some questions. Yeah.
Do you see the Q&A option, or only I see it?
Haven't.
Okay, so
No, I haven't
so
seen
I
that.
can I will copy paste the question into the chat, and also Mao, if you are here, you can also ask the question live too.
Yes.
This is the questions I just copied.
Okay, so the question is, you have mentioned the difference of spatial and spectral genus for the time series that each time step the graph topology is same. Will spatial genus and spectral genus perform differently? Okay, so for this question, I think it very depends, because in some real world scenarios, the spatial dependencies between time series may change differently. For example, sometimes since A and B may correlated at the specific times step, for example, positively correlated, but at another time step that's negatively correlated. So for these scenarios, normally the spectral genus will perform better, because the spatial genus cannot actually capture the negative correlated dependencies, because this is related to how we learn the graph structure. In most cases, we learn that based on a certain kind of similarities. So those similarities only capture the extent of the correlation between them, but cannot hack the directions, for example, positively or negatively. So in that case, spectral genus beyond the low pass filtering can help you to better model that dependencies. And for the second question, the time series of graphic neural networks, usually what kind of pooling is recommended? Well, so normally as you mentioned, normally we use the average pooling or max pooling, but in most cases, maybe average pooling should be sufficient. From what I can see in many research, and where the choice of pooling influence well contrastive learning. Okay, so for the rest part of the question, I think it's too specific that I'm afraid that I cannot give you a sure answer. Normally we have to give a try on, because on different data sets that may have different effect of the choice of the pooling. In fact, the performance, especially you mentioned the contrastive learning or something related to that. Yeah. Oh, good. Okay, then I will keep going. All right, so in time to graph plus, the quality that each time series, as you can see here, is transformed into graph with shiplets. Shiplets, that means different parts of, in this time series, I mean, to form the node, and the transition probabilities create the edge. So you have each time series to a graph, and then you use the GAT to capture the underlying correlations, followed by pooling operation. For example, you just use the average pooling, and to get the global representation of this time series, and then with that representation, you can do the classification, right? And the second one, it's still doing the univariate time series classification, but it's used the series as node. So given a specific data set, for each of the sample, we create a node here, and this graph is related to this data set. And in this case, for each of the time series, we will use some backbone model here to be as the feature extractor. Then we have the node features. And then we have the GNN modules opt-in to capture the dependencies between those nodes. And then for each of the node, you have the node embedding, and you use that to represent each of the time series in your data set, and then you do the classification. So that's the underlying idea. Okay. And the last one is the range job. So this is the very representative work for the multivariate time series classification, especially under the situation of irregularly sampled. So the core idea is, given a multivariate time series like this, you have different variables like blood pressure, blood test, etc. Your observation is irregularly sampled. So that means for example, at this point of time, only this observation is available. And at this point in time, another observation is available. So based on such a situation, how I can do the multivariate time series classification, like I want to classify this time evolving graph to a specific class. The key idea is, when we have an observation available, it will trigger an propagation. So the information at this time will propagate to the neighboring node. And then if you want to do the classification at this point of time, you can do that. Okay, so the information is continuous updating with the continuously available observations here. So that is the key concept behind the range job. Okay, so now I will briefly discuss the GNN for time series anomaly detections, because so far we discussed the forecasting, we discussed the classification, and for anomaly detection here, we unified them into a discrepancy framework. So whatever of the method, by using the graph neural network for time series anomaly, either using the, for example, reconstruction discrepancy or forecasting discrepancy or other kind of things like the relational discrepancy or hybrid or other kind of things. And for the reconstruction discrepancy, the underlying assumption is that the reconstructed error should be low during the normal period, but high during the anomalous period. So this is the reconstruction error in many cases, especially for the previous other works that related to the anomaly detection. So I think this is very easy to be understood. And forecast discrepancy is that we using the available information till the current time, we do the one step ahead forecasting, and then we compare the forecasted result with the ground truth to calculate certain discrepancies and to see whether the data at the current time t is anomaly or not. So that is the basic idea behind the forecasting-based discrepancy calculation. And for the relational discrepancy, it's more or less related to the relationship between variables. So we see the time series in a multivariate time series, its structure, its graph structure related things. And of course, you could combine them together. For example, relational plus the forecast discrepancies in your framework to do the anomaly detection. That's also possible. Here is the summary of the existing work. There are still some of them. For example, a very classic work, GDN, and another work, VGCRN, and CSTGL. So these three are very representative works that I will mainly cover in this talk. And for the strategy, this column is different from different from in the previous tables, and the RC, FC, RL, and CL represent different discrepancies, like the reconstruction, forecast, relational, and the class. So that the different ways you measure the difference between your prediction and the ground truth to calculate the anomaly score. Okay, so this is the high-level architecture of the GDN. So in this model, given the input multivariate time series, we first learn the graph structure, of course, and then we use graph attention based forecasting model here. We give the one step ahead forecasting, and then we compare our forecast with the ground truth observation, and based on that, we calculate the forecast discrepancy. So this is very straightforward, but works very well in the real world scenario. And the second one is called the VGCRN. So it's a little bit more complex. The pipeline is given the input multivariate time series. We first do some pre-processing. Sorry, it's 1 hour long. Okay.
Yeah. Just a quick note. So like I'm available to stay here as well, and then we'll keep the recording going. But if anybody who has a time commitment elsewhere, like feel free to watch the recording too. And thank you so much for the excellent talk and staying up to give us this talk. So feel free to the talk and finish it.
Okay, thank you. Okay, so in this work, we have two branches. So the upper branch is to calculate some forecasting related discrepancy. And the lower branch is using the autoencoder, as you can see, it's to reconstruct the input information. So this is the reconstruct discrepancy related calculation. So we use certain strategies here. We fuse two discrepancy calculations before we make the final anomaly detection in the given input. So that's the core idea, that combine different discrepancies together. And this work, CSTGL, that's another recent work to use the forecasted discrepancies to do the anomaly detection in multivariate time series. But the key difference is in this part. So the part 1 and the part 2 are similar in the previous work. And this part, the forecasting discrepancy, is also similar to the GDN, but with different technical details. And this part, the root cause anomaly diagnosis, I think is the highlight in this work, that it allows you to understand which kind of variables or the information that triggered such anomaly detection. I think in real world operations, sometimes we need the interpretation, and this could be a very helpful point to tackle this kind of issue. And for the time series imputation, there were two aspects. The one is task categorization. So as I mentioned, you could do the in-sample imputation or out-of-sample imputation. And the difference is that this one, it involves fitting the missing values within the given time series data, but this one will be the imputation in disjoint time series. Okay, and for the methodology, it could be deterministic or probabilistic. But anyway, as you can see that the imputation is actually kind of a generation process. We want to generate the missing value here. So as you maybe imagine that some recent technique like the diffusion model, is that possible to do that? The short answer is yes. And if you use the diffusion model, that could be understood as the probabilistic imputation. I will show you an example. But before that, here is the summarization of the recent works related to that. And not too many, but I think this is another very promising directions to work on. And for this column, inductiveness, this indicates whether a method can generate two unseen nodes or not. So this one, I think, is slightly different from the columns in previous table. Okay, so here I will mainly introduce two representative works. The one is called the green. And in this method, actually there were two branches again. And the upper branch is known as the forward process. And the lower branch is a sort of backward process, but they're actually mirrored with each other. So I will just illustrate the calculation in the upper branch. And the key difference is here. So this is from the historical data to the current data, but this one, the calculation is backward. Okay, so this is more or less related to, I think it's similar to the bidirectional calculation. Okay, so for in the upper branch, firstly, we define some spatial temporal graph neural networks to do the encoding. So in their implementation, this is message passing GRU. Okay, and this will it will summarize the historical information to give you the representations. So based on that, you could have the first stage imputation completed. So with the missing value in the greens, in the red node, to impute that with the yellow colors that denotes the first stage imputation. And after that, based on so this is actually the predictions of the current time, right? So based on that, they employ one additional MPNN, message passing neural network layer, to get the second stage imputation result. So that is the representation that can be combined with the second branch's result through a fusion layer, for example, MLP, to get the final deterministic imputation result. So this result is deterministic as we may commonly use that after a certain calculation, we have a specific value to be as the imputations. But this work is slightly different. So it's compared. So this is an overview by comparing this pre-STI work with two of the historical work. The one is green that we introduced, and another one CSDI. And the highlight in this work, in this pre-STI, we find that, so in short, it's based on the diffusion model, okay? And on the bottom process, that is the reverse process in the diffusion model that recover the noise to the imputed values. And as we know that the diffusion process is kind of the generation process. So this result is actually a kind of probabilistic imputations. So this is two very representative works up to date, hopefully, related to the graph neural networks for time series anomaly detection. And the third part, I will highlight some applications as well as the future directions. So the first one is the smart transportations. There were many use cases in real world, whatever, in the urban transportations or the other kind of downstream tasks that could be possible, like as you can see in this picture, right? So we have already discussed some, so I will omit here. And the second one is for the environment and sustainable energies. Okay, so this is a work known as the graph cast. So this use the spatial temporal graph related techniques to model the global climate and do some related downstream tasks that beyond the forecasting. And we could also do something related to the sustainable energy, like what I gave an example that in the wind farm that you can predict the power generations in each of the plants. Okay, and for the healthcare, there were also some very significant, always say well-established applications like the sleep stage classification, that you can classify a given EEG signals and to a specific sleep stage, like WN1 and 2 or something. And here is another one called the fraud detection. I think we're already very familiar with this kind of applications. So like given a transaction payment here, model that spatial temporal graphs that we can classify whether this is a fraud or not by calculating some score. And here's some future directions. I think this is very very exciting a very exciting direction that related to the pre-training transfer learning and large models. We both know that recently the foundation model as well as the large language model are very popular. But in the time series domain, there is still no very straightforward, or we say very prominent progress. So how we can, for example, using the time series data and spatial temporal data, how we can build a foundation model or repurposing the existing large models for both general purpose and domain specific applications. So the general purpose of the task is what we have covered today, like forecasting, classification, etc. And domain-specific application could be climate modeling that I mentioned, clinic question answering, like given the EEG signal, how you can do some Q&A, and urban computing, video reasoning, etc. So that a lot of things that we can do. And another direction is the uncertainty quantification. So in many real-world scenarios, merely given the deterministic, for example, forecasting or other kind of predictions, that's not enough in some scenario like weather forecasting. If, for example, if the weather on tomorrow is predicted to be rainy, how likely it's to be raining? So in some use case, we want to know how exactly the model are confident in giving the prediction, and what are the possible range of the predictions like this. We know that at this point of time, the model are not very confident, and this could be the possible ranges. So the uncertainty quantification could also be a valuable research directions in the future. And the last one I highlight here is the scalability, because nowadays people are trying to construct the larger and larger spatial temporal data. I mean, not only the volume of the data, but also the scale of the data. For example, the size of the underlying graph. There are an increasing number of nodes, ages, and the degree. So toward the large models of the genius for time series, how we can make the existing, for example, graph operations that scale well on those large scale data that remains very a very big challenge, I would say, like how we can do that before we move to the, for example, the large foundation models for the GNN for time series. And conclusion. So what do we have covered today? So firstly, I give a brief introduction of the taxonomy of the graph neural network for time series, and also give an overview of the GNN for time series with some examples, like what are the typical works in the existing literatures and what we have learned from them. And then I discussed some applications like the transportation, climate modeling, and fraud detection, as well as 3 very promising research directions like the large models, uncertainty quantifications, as well as the scalability of the existing methods. So that's pretty much that I want to share on today's presentation. Sorry, it's a little bit long. So if you want to know more details, you could find our papers here as well as our GitHub page. So we will try our best to update them frequently. So thank you so much for attending today's session.
Thank you so much for the great presentation, Ming. Is there any question from the audience before we wrap up? And I also find the future direction that you mentioned like very interesting, like the foundational model and so on. But it's not as trivial as like NLPs, because time series data are very domain specific, I guess. Same with graphs, like different category of graphs are completely different. So if you train on many social networks, doesn't mean that it will work for like other type of graphs. So I guess like that's one of the challenges. But yeah, thank you so much. And and we'll put the talk like up on YouTube. So if you want to like rewatch like specific parts, you can find it too. And the slides are also available on the website. Thanks, the speaker again. Yeah, see you next week at the reading group.
Thank you, Andy, and thank you, everyone.